Hello, now we will talk about the compressed liquid states. Let's first recall where the compressed liquid region is located on the TV diagram. So this is the TV diagram. This is the vapor dome, and let's say this is the critical temperature. So the compressed liquid region is located to the left of the saturated liquid line. So this is the saturated liquid line and is located to the left of the saturated liquid line. So the compressed or subcooled liquid region is located to the left of the saturated liquid line. Okay, so in order to know what are the conditions for a given state to be classified as a compressed liquid state, so conditions for compressed liquid state, the first one, the pressure should be higher than the saturation pressure for a given temperature. So this is evident when we draw the PV diagram. So this is the PV diagram. So in a PV diagram we draw lines of constant temperature. So at this line here we have the saturation pressure when we have phase change, and for the state to be in the compressed liquid region, it should have a pressure P that is higher than the saturation pressure. So in this region the pressure is higher than the saturation pressure as opposed to the superheated region. If we recall, the pressure in the superheated region is lower than the saturation pressure. So this is the first condition. The second condition, the temperature in the compressed liquid region is less than the saturation temperature for a given pressure. So also we can show this on a PV diagram. This is, sorry, on a TV diagram. So this is the line of constant pressure, and this temperature here is the saturation temperature, and in the compressed liquid region we should have a temperature that is lower than the saturation temperature. The third conditions are if the specific volume is less than Vf, or the internal energy is less than UF, or the, let's say, enthalpy is the enthalpy H is less than HF. So also, so this is the TV diagram, and this is the pressure, constant pressure curve, and this is Vf. So less than Vf, it means that we are to the left of the saturated liquid line. So any point here has a specific volume that is less than Vf, or it applies also to the internal energy and to the enthalpy. So mainly these are the conditions for the state to be classified as a compressed liquid state. For the compressed liquid table, so it is table A5 for water, a compressed liquid table, compressed liquid table. You can see the format of this table. So this is a table for the compressed liquid water, and it has a similar format to table A4, the superheated table. We have several tables for each one for different values of pressure, and the pressure for a given pressure, the properties, the specific volume, U, H, or S are listed against the temperature, and the saturated temperature is given between parentheses below the pressure values. So it should we should be careful here that the specific volume is also multiplied by 1000. So the values here, when extracted, should be multiplied by 10 to power minus 3. We should note that for the compressed liquid tables, mainly the compressed liquid table is not commonly available for substance. So compressed liquid tables, are not commonly available. So if you notice in the attached file of thermodynamic tables that come along with this course, you will only find a compressed liquid table for water, but you will not find this table available for other substances. The reason behind this that the properties in the compressed liquid region vary. So the properties in this region vary very little with pressure, and they are more dependent on temperature variation, on T. So giving this information, we can make approximations using saturated liquid data. The saturated liquid data are mainly the VF, so all properties denoted by a subscript F, VF, UF, and HF. So how we are going to do these approximations? So I will show you. Let's draw a TV diagram. So this is the vapor dome. If we draw a line of constant pressure, here P1, and we draw like another line of constant pressure at higher than P1, we can notice that in the compressed liquid region, the lines are very close to each other. So the pressure lines in the compressed liquid region, they are very close to each other. Since the variation of pressure have little effect on the variation of properties. So let's say this is the volume P2, this is the volume, if we draw, this is the volume V3, and this is Vf. So increasing the pressure will decrease will decrease the specific volume in a very small way. So the change in increasing the pressure will decrease the specific volume very little in this case. So we can make this approximation. We can say that the specific volume V can be approximated as this value Vf at a given temperature T. So we can say the specific volume V can be approximated to Vf at a given temperature. So the variation of pressure has very reduced effect. So to give you an idea, like if increasing the pressure 100 times will cause the properties to change by less than 1%. So we can say the specific volume V is approximately equal to Vf at a given temperature. Also for the internal energy U, we can say that is approximately equal to Uf at a given T. However, for the enthalpy H, we know that H is equal to U plus PV, and approximately we said U that approximately equal to Uf at T plus P, and V is equal to Vf at T. So let's see what HF is equal to. So HF will be equal to not approximately, will be equal to, so HF is equal to Uf plus the pressure at the saturated liquid is equal to the saturation pressure into Vf. So HF at a given temperature is equal to Uf at a given temperature plus P saturation times Vf. If we subtract these two equations, we'll obtain H minus HF is equal to P minus P sat into Vf. So H will be approximately equal to HF at T plus P minus P sat at Vf. So for the enthalpy, as you notice, we have this additional term. If this additional term, if P minus P sat into the specific volume Vf is small, and usually it is a small value since Vf as a value is small, but if it is small, then we can neglect this term and say that also H as an enthalpy is equal to HF at T. So as a conclusion, instead of using the compressed liquid table we can use the saturated liquid data. Rated liquid data available in table, for example for water in table A3. Why A2. Why A2? So available in table A2, the temperature table. Since our approximation is mainly dependent on the temperature, we said that V is approximately equal to Vf at a given T. So if we know the temperature, we go to the temperature table and we read Vf. Also U is Uf at a given T, and H we can say is Hf at a given T, given that P minus P sat into Vf is small. So to show you what we are talking about, we're going to solve an example by calculating the properties using one time using the compressed liquid table, and another way using the saturated temperature table, and we will see the difference. So let's say we want to determine the internal energy U for compressed. So we want to determine U for compressed liquid water, at a temperature which is equal to 80 degrees Celsius and the pressure of 5 megapascal. And let's calculate it first using table A5, and second using table A2, and in part C let's see the error between the two. Okay, so at a pressure of 5 megapascal, let's go to table A5, part A. Let's go to table A5, 5 mega and a temperature of 80 degrees. So this is the pressure of 5 mega, and for boiling to start to occur, the saturation temperature at 5 megapascal or 50 bar should be 263.99. The temperature here is 80 degrees, which is less than the saturation temperature. Then this is of course a compressed liquid state. So at 80 degree, the internal energy is 333.72 kilojoule per kilogram. So from table A5, U the 333.72 kilojoule per kilogram. Let's say we don't have the compressed liquid table, and we're only left with the saturated liquid vapor table. So we will use the temperature table, as we said, A2. Since now we're at a temperature of 80 degrees Celsius, so we go to at 80 degrees here, the internal energy U will be equal to UF 334.86. So 300 U is approximately equal to UF at T equal to 80 degrees Celsius, and is equal to 334.86 kilojoule per kilogram. So as you can see, this value is very close to the more accurate value, 333.72. so we have like a difference of 1 kilojoule per kilogram. So if you want to calculate, let's say the error will be equal to 334.86 minus 333.72 divided by the accurate value 333.72 times 100. So it is approximately of 0.34%. So you have an error which is less than 1%. So using table A2 for compressed liquid data is accurate also.